So today we will start talking about modulation in wireless networks. So this is something similar to line coding in wired networks which we've already studied, but it's a little bit more complicated because of the situations in wireless networks. So now let's say you have a sender, he has an antenna and he wants to send to somebody else. This is the receiver. So he has to send some signal over to the receiver. Now what signal is he going to send? So first of all, it can't be a free for all because unlike a wired situation where there is maybe a dedicated wire between the sender and the receiver, in which case they don't have to worry about who else is transmitting, around them. Here, there is a problem that if somebody else is transmitting and sending out signals, it would interfere with this particular signal. So how do we deal with this? How do we reduce the interference? So the government has solutions. They have to step in, and this is where the whole business of spectrum auctions and things like that come up. So let's think about it. So we have a spectrum band over here. This is the zero frequency, and we know that if somebody transmits a signal in one band, let's say that this is the Fourier transform of the signal that he's transmitting, right? It's looking at the same signal but in the frequency domain, and let's say it looks something like this. Most of the signal is in this band, and somebody else comes along and he transmits another signal in a different band. So this is what his Fourier transform would look like of his signal. Then you can design some circuits at the receiver of any one of these signals so that it can filter out the other one. So I can have, let's say, some sort of a band pass filter which is only going to take this out, this particular signal. So remember the terminology of from the last class. Low pass filter is saying that I take all low frequencies up to a certain cutoff. High pass filter is saying the filter removes all frequencies below a cutoff and it lets through the high frequency. Band pass is saying that I sort of do a combination of those. I take only a particular range of frequency, a particular band out, and this is what is there in all your radios. So by ensuring that different signals, let's say neighboring wireless transmitters transmit at different frequencies, we can prevent their interfering with each other. Okay, so each receiver, suppose this is A who's transmitting to B, and this is C who is transmitting to D. Okay. So I'm just saying these are antennas. So C is transmitting to D. If A and B are using this band, if A is using this band to transmit and C is using this band, then B has to have a filter which only takes out this signal. It removes that, and D has to use a filter over here. So the question is, how do you do this? How do you ensure that a particular signal is within a band? That's something we have to think about. But anyway, what the government does is they auction different parts of the spectrum. So all the frequency range is called spectrum. You will read that in the newspapers. So the Minister of Communications recently talked about auctioning 5G spectrum. So anyway, so it's just a particular range of frequencies and the government auctions it typically, and the highest bidder gets to use it. Okay, so maybe Airtel gets a particular band, maybe 20 megahertz or 40 megahertz, whatever. Right? Geo gets another band, non-overlapping band, and so on. Right? And each of them is told to transmit only within that band. Okay? Of course, we are also lucky that there are certain unlicensed bands, like for Wi-Fi. So nobody needs a license, nobody pays any spectrum fees, but then interference becomes a problem. So in Wi-Fi we have to have specific methods to reduce the interference, and we'll study that when we talk about the link layer. But now we have this basic problem. Suppose the government has given us a frequency band. They say F0 is your center frequency. Maybe it is, let's say, 1 gigahertz or whatever, right? 2 gigahertz, whatever. And they tell you, you had better keep your signal within this much of a band around this center frequency. So how are we going to do that? So whatever this frequencies they will tell us, and they will say you have plus or minus 10 megahertz, let's say, around this. And if you take the Fourier transform of whatever you transmit, it should lie, most of it should lie within this band, and very little should go outside. Okay, so this small amount cannot be avoided. You can show in theory it's impossible to have a signal which is limited in time and in frequency. Okay, that's possible to show. So there will be a little bit of spillover into the neighboring bands, but as long as it's small enough, it won't affect the other people much. So first of all, how do we get a signal within this band? Right, so I'm just giving an example. This is 20 megahertz. So one way to do it is that you use a sine wave. So suppose I take a sine wave like this. What is its Fourier transform going to be like? Okay, so I'm just putting 0 over here, and this is F0. So this particular sine wave will have, in theory, all its energy concentrated at F0. So this is good. I mean, so and intuitively it makes sense, right? You have a sine wave or a cosine at frequency F0. Okay, so t is the time, and this is the frequency. So obviously its energy has to be completely at F0. So we can transmit this, and the government wouldn't be upset, because all our energy is within that band. Right? We have to say it's between plus or minus something around F0. Now the problem here is that this doesn't convey any information. So if I'm transmitting a cosine continuously, let's say A is transmitting to B just a cosine, what information is he sending? Is it a 1 or a 0 or what? And clearly there's no information in it. So what he has to do is he has to modify this signal in some way, and that is where the term modulation comes in. So we have to change this signal in some way to convey whether it's a bit 0 or a 1. Okay. So how could we do this? Well, one way to do it is that we change, let's say suppose our base signal is something like this, what is called a carrier signal. So how can we change this? So we can think about it. So suppose you have put in an amplitude over here, and you also put in a phase. And this is the amplitude. And this is the phase. So the question is, can I change the amplitude or can I change the phase and convey information in some way? Okay. So we will look at ways in which this is done typically in wireless systems, in high-speed wireless systems like Wi-Fi and 4G, 5G technologies and so on. You would do something like this. It's also possible to change the frequency. So you can, for example, change this frequency itself to convey some information, and that is what is used in FM. So we won't be considering that, but FM stands for frequency modulation. Okay. But FM is used, of course, for analog communications. I mean, meaning that you don't have bit zeros and ones. So when we talk about digital communication, the information is in terms of zeros and ones. But in analog, which we won't be considering here, you just have some signal which varies over time. It's not zeros and ones. Like let's say that this is a voice signal or whatever, right? It's a, let's say somebody is singing a song and you want to send that in terms of as a radio signal. So this is the signal, and you have to use this signal to somehow send it over this carrier frequency. Okay. Anyway, so this is something we won't be considering. We'll only focus on the case where you have information in terms of zeros and ones and you want to communicate that across. It's not a continuously varying signal like you have in analog communication. Okay, so one way to do it is I have a particular phase to show 0 and a particular phase to show 1. Okay, and I keep changing that over time. And it's also possible that I could vary the amplitude, so that too is done in certain modulation schemes. So let's think about it. How do we visually think about this? So maybe before we look at mathematics, let's just draw what this would look like, cosine. So suppose I have cos 2 pi f0 t, it would look like this. Okay. And where this is one time period. Okay, so one time period would be one wavelength, it would be 1 over f0. Okay. And suppose I change the phase by 180 degrees. What would it be? So changing the phase by 180 degrees is essentially jumping over here, so it would look something like this. Okay, and so I would have So this, what I could do is, for example, I can send a bit, let's say a bit 0 here and a bit 1 over here in this way. This is one simple way to do it. So the signal is like this. Let's say the bit is 1 and bit is 0, I send this out. If the next bit is 1, I would send this signal out. And again, if the bit is 0, then I go back to this signal. So the receiver wants to know which of these was sent, and based on that he decides whether it was a 1 or a 0. Okay. Now you can show that with these sorts of modulation schemes, the Fourier transform is going to lie within a band around f0. Okay, so this signal, because I am varying the signal, it's not exactly concentrated only at f0. It's not. This is not exactly a sinusoid, just a plain sinusoid, because I'm changing the phase suddenly over here in between the signal. So I can, but it can be shown that the Fourier transform of this will look something like this, around f0. Okay. And the width of this signal in the frequency domain, which is essentially saying how much of this, how wide this is going to be around f0, depends on how often you change this particular frequency. Okay, so I beg your pardon, how often you change the phase. Okay, so here I've shown that we are changing the phase every one time period. Okay, so every one wavelength we are changing it, which may be quite fast actually. Actually, this is going to be very wide. So what you would want to do in practice is that you would have several wavelengths where the phase stays the same. Let's say like this, 4 wavelengths, and then you change the phase. Okay, I think we need one more, right? Okay, so this is corresponds to bit 0 and this corresponds to bit 1. And in this case, because I am changing the phase only more rarely, this is going to be much narrower than in this particular case, right? So this was the Fourier transform of this particular signal. Then the Fourier transform of this particular signal is going to be much more narrow. It's going to be something like this. Okay, and you would expect that the width of this to be 1/4 the width of the Fourier transform of this signal. Okay, just because we are changing the phase very rarely here compared to this. Okay, so of course these are examples, and we'd have to make a choice what we are going to do, how often we are going to change this. So here we are sending less information per time, because we are only sending 1 bit every 4 wavelengths. Here you are sending 1 bit every wavelength. But there are advantages to sending data slowly, that we are sending data in a much narrower band. Okay. So the government gives you 20 megahertz, then great, you can send at a high data rate. But if it gives you only, let's say, 5 megahertz, then you have to send at 1/4 the rate, okay, intuitively. So how do we analyze these sorts of systems? We want to do things like figure out the bit error rate. So this is a very key thing, and as you've seen from your own experiments that you've done, you've seen that signal strength can be quite low in a wireless system, something like even -100 dBm or minus 80 dBm can be a good signal, right? And -80 dBm we know is a very small power received at the receiver. So we want to know what is the bit error rate going to be, because suppose I transmit a signal S of t. This is the signal that the modulated signal, I'm changing, let's say, the amplitude or the phase or something like that to send out information. What I get, so this is what I'm transmitting. So what is received? So first of all, in a more general case, you have, maybe let's give you the most general case, though we will not go into the details, but just for your information. So you can get all the details if you take a communications class or an advanced communications class. But the most general case is what I receive at, let's say I have R of t at the receiver, is going to be a set of reflections. You know, we said there's going to be multipath. Here is an antenna at the sender and the receiver. This is the sender, this is the receiver. So the signal might have a direct line of sight component. But if you look from this antenna, you can actually see this one. But there are also reflections, like we said. So how do we model all of this? Where we say that there are different reflections, number of components. Each of them attenuates the signal by a certain amount, but also delays it by a certain amount. Okay, so the received signal is not just the direct line of sight signal, but there are many components. Each of them attenuates the signal by a little bit, but also the delays are a little bit more, right? Depending on the situation. So these taus are not the same for all components. Plus there is some noise, and this noise is actually not necessarily coming from the external environment, but it's inbuilt in the circuits that you have with the receiver. So there is something called white noise, and when it gets added, so this gets added, the term is additive white Gaussian noise. Okay, so AWGN is what people talk about. Okay, but this is the most general case. Okay, and you can see it's very, very tricky in a wireless system. How do you even know how many reflections there are going to be? This could be a tree which is shaking. So maybe this actually changes over time, right? And you know, maybe this sender is himself moving, right, in a car or something like that. So all these reflections are continuously changing over time. So the receiver has to do a lot of work, you know, to figure out what these reflections are and tries to figure out what was the signal received. Okay, so we are not going to go into all these details, but I just thought I'll mention this so that you know the complexity involved. But how do we analyze this sort of situation? Because before you spend so much of money building a 4G technology or, you know, putting it in handsets and so on, you should have some theoretical idea of how it's going to perform. So ideally you want your bit error rate to be as small as possible. So what is bit error rate? It's the fraction of transmitted bits which are received in error. Fraction of transmitted bits received in error. Okay, you want this to be as close to 0 as possible. Okay, because every time you have a bit in error, it's going to affect what was received. I mean, you can't, there are certain applications which cannot tolerate even a single bit error, because of which there will have to be some mechanism to deal with this bit error rate. And you have to either have redundant information being sent continuously using some sort of coding technique. Otherwise, the higher layers will have to deal with it and retransmit the information again. Okay, so that's all a pain. So you want to reduce this as much as possible. But how do we theoretically analyze this? And there is a very nice way to think about all this, which is in terms of vector spaces. So the first time I heard about this, it seemed very counterintuitive. I mean, what has this got to do with vector spaces at all? So the traditional vector spaces that we have, like we studied in school, you have an x component, you have a x-axis, y-axis, and a z-axis. And each vector is given as, let's say, Vx, Vy, Vz, right? Something like this. And suppose you want to know what is the x component of a given vector, you just take its dot product. I beg your pardon. So it's a V dot product of V with the unit vector in the x direction. So I'm going to call it Ex. And similarly for Vy would be dot product of V with Ey and so on. Okay, and Vz so right. So this is the traditional vector space that we are all used to. So what has this got to do at all with the signals that we are transmitting? It turns out that you can write these signals also in a vector space. So how do we do this? And actually this is a well-developed field. I mean, it's an old mathematical field, and it's called functional analysis and so on, right? So some of you who are doing advanced mathematics, well, maybe part of mathematics Olympiad or whatever, you will study that, or maybe you've already studied it. And in fact, your Fourier analysis, which you studied in physics, is already looking at that in some manner. Okay, so how do we look at this? So suppose I want to look at all frequencies around f0. So I want to focus on frequency f0, since we seem to be sending out signals only which is a sinusoid at that frequency, but we change the phase or the amplitude a little bit here and there. So I am going to draw a vector space where I have, let's say it's a two-dimensional vector space. And in this vector space, I am going to any point here in this vector space. Okay, let's say that it has amplitude A and angle theta over here in this vector space. This particular vector corresponds to a signal which is A cosine 2 pi f0 t minus theta. Let's say I do it this way. Okay, and let me just see. Okay, so suppose I do it that way. So essentially any signal that I am transmitting can be represented as a point in this vector space. Right? If I change theta, I mean this particular vector is going to be at a different position, right, a different angle. And if I change the amplitude, it's also going to change a little. Okay. So this is a particular signal in the time domain. Okay, so let's say I'm transmitting the signal over some time period. Okay, let's say that let's say this is my signal. Whatever, right? Something like this. And this signal I am mapping to a point. So in this particular vector space. So my transmitted signal can be represented as a point here, and hopefully even my received signal will be represented by as a point over here, okay, which is going to make it very simple for us to decode what bits were transmitted. Okay, so what does it mean here? So we managed to draw these signals as points over here, but is there an analogous notion of this dot product? Okay. And that is going to be very key over here. To get an idea about what this dot product is going to mean over here, let's think about what these unit vectors are going to be. Because as we saw earlier, dot product, you have to find the x component or the y component and so on. We had to take the dot product with these unit vectors individually. Okay. So what could be something like an equivalent of a unit vector in the x direction or the y direction? So let's think, what if I had a point on only the x-axis? What if I had a point here? What would it be? What would it look like? It would be, there would be some constant times cosine 2 pi f0 t. So the phase is 0. Right? And what if I had a point over here on this? Well, it's going to be some constant cos 2 pi f0 t minus pi by 2. And this is nothing but a sine wave, sine 2 pi f0 t. Okay. So the unit vector is going to be just some multiple of sine wave in the y direction, and the unit vector here is going to be just a multiple of cosine. Okay, and of course we'll have to normalize it in some way depending on how we define that dot product. Okay, but effectively what we've ended up with is a vector space where we have an x component which corresponds to cosine, and y component corresponding to sine wave, sine 2 pi f0 t. And any point here is, any vector over here can be represented as a sum of cosine and sine. Okay, so whatever I have here can be right. So you can just think about, why do I have that? Well, if you expand this particular cosine using your standard 12 standard maths, right, you can write it as it's like cos A minus B, right? You can write it in terms of cos A cos B plus sin A sin B or whatever, right? And that's essentially a sum of cosine and sine of this particular frequency. Okay. So that's what we have. So how do we get the dot product? Yeah, let me just complete this. Sum of sine 2 pi f0 t and cosine 2 pi f0 t. So the way we define a dot product is like this. In these functional sort of vector spaces where we are representing functions as a vector, is that your dot product is just an integral. Okay. So it's sort of like an extension of what we have here. Here you just have three components of the vector space. Here you have a signal which has lots of values for different time instants. So what I'm going to do is I'm going to take to find, suppose I have two functions and g of t, and let's say that they go from 0 to t. So right, so this is one bit period in our example. Okay, and so f of t is some function over here and g of t is another function, let's say. So in these functional spaces, to take the inner dot product, okay, so I just integrate the signal okay, and that gives me the dot product. Sometimes the dot product is called the inner product. Okay. So of course this is the engineers, communication engineers use complex numbers, right, to make this. So to simplify things, so the definition would actually have like a complex conjugate too, but we'll ignore that for the time. Okay. Anyway, so suppose you have a particular signal and you want to find its x component or y component over here in this particular vector space. How would you do it? Okay, so what you would do is, suppose this is my received signal. What I would do is I find the x component, which is just the dot product of r of t with the unit vector over here, and then I find the y component, that's just the dot product of what I receive and the y component. Okay, and we know that Ex is just some constant times the cosine, and Ey is equal to some constant times the sine. And the question is what this constant is. We'll look at that in a minute. So essentially what you're going to do is you're going to calculate this. You're going to actually evaluate this integral in order to get the x and the y components. So let's think for a moment, what is this constant going to be? So I want the dot product of Ex with itself to be equal to 1. Okay, so what is this going to be? So let's just see what is, let's just call this some constant c. Okay. So suppose my signal is being sent over a certain number of wavelengths. So let's say that I'm sending it from 0 to t, which is equal to n wavelengths. So this is my cosine, okay, and I'm sending it out over a particular time period. And so on, right? Whatever, right? In general, I'm sending my signal out for this long. Okay, so I think here it was a little bit different. I had sent a sine over here rather than a cosine anyway. So let's suppose my signal is something like this. So what is, I want my inner product, so I'm going to integrate from 0 to t c times cos 2 pi f0 t times c times cos 2 pi f0 t dt. Okay. So I end up with c square integral 0 to t cos square 2 pi f0 t dt. And what is this? Well, it is, we end up with c square 1 plus cos 4 pi f0 t divided by 2 dt. So what does this become? So this over here is what? That's what we have to think. Now this is just a cosine with twice the frequency at which we were sending the signal. And t is a multiple of number of wavelengths. So what is that this signal going to integrate to? So integral 0 to t cos 4 pi f0 t dt. Okay, so that is a cosine which is going like this, and it's a multiple of its wavelengths, right? So we're going from 0 to t. So if you integrate a cosine over one wavelength, it goes to 0, right? And if you integrate over multiple wavelengths, again it's going to go to 0. So we end up with 0. So this term goes to 0. So what we are left with is just half. So that is c square times half times t. Okay. And this I want to be equal to 1 because I want this is the dot product of this is what I am calling my unit vector in the x direction. So what is c going to be equal to? That's what we were really after. So c is equal to 2 by t root 2 by t, which is, and we said t is just n over f0. Okay, so in the most general case, it's going to be 2 f0 divided by n. Okay, fine. Okay, so just to write that down again, Ex is c times cosine 2 pi f0 t. Okay, and which is just root 2 f0 by n, okay, cos 2 pi f0 t. and we can extend this EY is just the same thing, but we're going to have sine 2 pi f0 t. Okay, so in general, when you have a particular signal that you get, if you want to find its x and y coordinates, you will have to take the dot product with these unit vectors in the x and y direction. Okay, so I can draw this. Suppose I have a signal which I am going to receive. Okay, and so let's say R of t is the signal that I receive. So what I'm going to do is I'm going to find out its x and y coordinates. And essentially Rx and Ry is just the inner product of my signal with the x unit vector, and Ry is the inner product with the y unit vector. Okay, so why are we doing all of this, right? We are after the bit error rate. We want to find out what is the bit error rate, and we are going to not look at the general case where you have arbitrary number of multipath components and so on. That's very a more complicated situation. So let's say that my received signal is some attenuated version of the sent signal. Okay, I'm forgetting about multiple paths and so on. Just one path, and there is some attenuation. Plus noise, and this is additive white Gaussian noise. Okay, so this Gaussian noise has some particular characteristics, and one of them is that when you plot the noise over here in this vector space, it's going to have certain x and y components, each of which is a random variable given by a Gaussian distribution. So we'll just write that down. So what is Rx going to be? It's just going to be A times dot product of the transmitted signal with the unit vector in the x direction plus dot product of the noise with the unit vector. Okay, and similarly the y component is the dot product with y with this. Okay, and I'm going to call this nx and this is ny. Okay, so what is happening in the time domain is very tricky. So this is my signal which I was sending out. Let's say it looked something like this. So this is actually a sine wave, right? Sine it's like sine 2 pi f0 t. Okay, but of course the time period of 1 bit, so this is t is the time period of 1 bit. So this is what I'm sending out, and then I get an attenuated version of it. So this is what is being obtained at the receiver. So it's an attenuated version. plus there is some noise getting added. So this noise is totally unpredictable. So I don't know in advance what the noise is going to be. So to summarize, a signal ST when it's sent across gets attenuated by factor A, and some additive white Gaussian noise gets added. Okay. So let's think what happens first of all when we look at these signals in the vector space. So let's go back up a little bit, and first of all let's look at the signal A cos 2 pi f0 t minus theta and see where it lies in this vector space. So we have Ex, we have a unit vector here, and of course the unit vector here is Ey. And we said that Ex is equal to essentially the cosine, but with this multiplicative factor. It became 2f0 by n cos 2 pi f0 t. And what would Ey be? Well, according to the way we defined it, we said on the y-axis the unit vector should be a multiple of sine 2 pi f0 t. And of course the normalization factor is the same one. So is it true that Ex, you take the dot product of Ex and Ey, so is this really 0? So let's think about it. So we said we have to integrate 0 to t, where we said t is n divided by f0. And what we said is we want to take the product of these two functions and integrate. Okay, so of course we end up with 2f0 by n cos 2 pi f0 t sine 2 pi f0 t dt. Okay. So what is this going to be? It's your trigonometric formulas, sine theta cos theta, right? You can write it in terms of sine 2 theta, right? And so we'll have 0 and naught. And so what do we get? Sine 4 pi f0 t by 2 dt. Okay. Now this is again another sinusoid, and we are integrating over a multiple of wavelengths of it. Okay, so this obviously should go to 0. Okay, the same reasoning that we had before. So indeed, these two unit vectors are going to be orthogonal to each other with this definition of inner product. Okay, so the question that I wanted to ask is, where is this particular function going to lie in this space? And earlier I said that it should have angle theta, and the length of it should be a, but let's check how correct that is. So suppose I just call this g of t, let's say. So what would be gx and gy? So the coordinates that I want to get over here, right? What is the x coordinate and y coordinate of this particular signal when I draw it as a point in this vector space? So g of t is nothing but a times cos theta cos 2 pi f0 t plus sin theta sin 2 pi f0 t, right? Expanding, and let's write it in terms of ex and ey, because we know, we are familiar with those. We know that ex dot product with itself should give 1. So we are left with a times cos theta ex plus sin theta ey, but we have to divide by this factor over here, root 2f0 by n. Okay. So let's think about it. What is gx going to be? What is gx and gy going to be? Okay, so gx is the dot product of g of t and ex which is a root n by 2f0 cos theta ex, right? I'm just expanding this and taking the dot product with each term. Okay, and plus sin theta dot product of ey with ex. So this goes to 0 from what we know, and this of course goes to 1. Okay, so we are left with a root n divided by 2f0 cos theta, that is gx. And what would gy be? Well, you just take the dot product with ey, so we are going to end up with sort of the opposite would happen. This term would disappear because we would be taking the dot product of ex with ey, whereas this would go to 1, and we'd end up with the same constant sin theta. Okay, so if I want to plot this, essentially what is it going to be? It's going to have angle theta, but this length is not going to be what I had said earlier. I wasn't taking into account the normalization, so it's going to be a root n by 2f0. Okay, so this is going to be the length of this. Okay. So our intuition was correct, which we started out. We said you have cos theta, cos 2 pi f0 t on this axis, sin 2 pi f0 t represented on this axis, and any linear combination of those could be represented by a point in this vector space. Okay. Okay, so what's going to happen when, suppose I transmit g of t and it gets attenuated? So, like that. Suppose uh, we transmit, let's make it simple. Let's say we transmit s of t is equal to a cos 2 pi f0 t. So, just as an exercise, where would this be in this vector space? It's going to be here on the x-axis. And what is this distance going to be? Well, we said it's going to be a root n by f0, 2f0. Okay, so this is a signal that I'm going to transmit, and let's actually go to a full modulation scheme. And so let's say that this corresponds to bit 0, and also suppose I wanted to send bit 1. Suppose I send this. So the signal that I am transmitting, let's call this S0t. If I am transmitting S0 of t when the bit is 0, and I am transmitting S1 of t, which is minus a cos 2 pi f0 t. Okay. So this corresponds to bit 1. Okay. And I am transmitting this for t between capital T and 0. Okay, so for one time period, and I said this is equal to n divided by f0. Okay. So for n wavelengths of this particular frequency, I am transmitting this particular signal. Okay, either of these. If I want to transmit a bit 0, I am sending out this signal. If I want to send bit 1, I send out this signal. Okay. So this second signal is going to have a point in this vector space exactly the opposite. Okay, opposite, but at this point over here. Okay, so this is the origin. Okay. So what I've shown over here is something called a constellation diagram. So constellation diagram shows you that the signals that you are transmitting, but in this sort of a vector space where I have cos on the x-axis and sine on the y-axis. Okay, and of course the unit vectors will be these functions multiplied by an appropriate constant. Okay, so this is a simple constellation diagram that I am showing for transmitting bit 0 and bit 1. The question is, what is going to happen at the receiver? Because what I get, so suppose I transmit signal s of t at the sender, we said that this gets transformed into a times s of t, so there's some attenuation plus noise. Okay. So what would happen in this case? So let's focus on this. What would this signal be in this constellation, in this sort of a vector space? So at the receiver, I have, suppose I transmit this signal. Okay, so let's say what this is, let's say corresponds to a S0t. So what is this distance going to be? Well, it's this same distance multiplied by small a. So a times a root n by 2f0. Okay. And you can verify that. You can actually take the dot product of this signal with Ex and so on. Okay, so this was the signal that I transmitted, but by the time it reached the receiver it got attenuated, so it actually shifted over here. Okay. And now there's another issue here. There's this noise which gets added, and we are just going to say that the components of the noise, Nx and Ny, are drawn from a Gaussian distribution. Okay, and so what did we see here? We said that this is the received signal. So we said that Rx is just A and whatever was transmitted. Let's just call the constellation point here Sx, Sy. This is the constellation point that was sent. So the x component of the received signal is A times Sx plus Nx, and the y component is A Sy plus Ny. Okay, so this is the general case for a general signal S of t. So in this case, in this example that I've looked at, Sy is 0. There is only an x component of whatever I'm transmitting, this constellation point. So it gets shifted over here, right? And the y component here, this is 0, this quantity over here is 0. But the noise pushes this in both directions. Okay, so just let me write that over here. One second. So the noise is going to push this in both directions. There's going to be an Nx component and an Ny component. Okay. So finally what I might end up with is something like this. Let's see, if I choose this. Okay. So just to summarize what has happened, so this is what I transmitted, but due to attenuation it reduced. The signal essentially reduced in amplitude, so it went down like this. Plus some noise got added, both in x and y coordinates. So it got pushed to this orange dot over here. So let's say this is Rx, R1. Okay, just because this noise pushed it in both directions. Okay. So suppose I sent this signal multiple number of times. Suppose I sent bit 0 lots and lots of times, and I wanted to see what would it look like in this vector space. How might that look? So suppose I sent it out. Okay. So this corresponds to this point. Okay, and this is A times A root n by 2f0. So suppose I sent S0 of t a million times. And I want to know what was received at the other end. So it will turn out that once, maybe let's say the first time you got something here, next time you got something here, right? So you'll get everything clustered around this point. However, noise is pushing it in both directions a little bit, because we are assuming the noise is not too much. Okay? And suppose I was transmitting, instead of sending S 0 of t, suppose I was sending S1 of t, okay, then let's say that this is the same, going to be at the same distance here. Because of attenuation, the signal comes down here, and then what's going to happen? Well, the noise is going to push this around, so it will be mostly clustered around this, but each component is an independent Gaussian distribution. Okay, so they are, I should write that down, Nx and Ny are IID Gaussian. Okay. And that is why this gets the name constellation diagram. So it looks like you have a constellation of stars, right, all around, centered around these particular points. So you transmit a signal, but noise pushes it out in both directions a little bit. Okay. So this is what we receive, and we wanted to calculate what is the bit error rate going to be like. Okay. And that's why we were looking at this. So first of all, let's see how you're going to detect what bit was transmitted. So detection at the receiver. So really the bit error that we get depends on how the receiver is going to detect the bits. So what we are going to say, suppose the received signal is like this. So this is what the receiver gets to see, R of t. So first of all, what he's going to do is he's going to calculate Rx and Ry. Okay. And we know the formula for that. Rx is just dot product of R of t with Ex. And Ry is going to be dot product with Ey. Okay. So how are we going to do this in practice? I mean, you're going to build a circuit to do this. Your circuit is automatically going to take this dot product. It's going to do the integration for you. Okay. So you actually build a physical circuit which will do this integration. So we'll not bother about how that is done, right? Let's just assume that the receiver gets Rx and Ry. So he gets some point over here in this two-dimensional plane. Okay. And now he has to decide whether it was this, whether it was S0 was transmitted or S1 was transmitted. Okay. So how are we going to do it? So you can think, suppose you were at the receiver and you had to decide whether it was a 0 or 1. How would you do it? Okay. So really what we want to do is we want to see, is this point, suppose this was what I received, is it closer to this point or is it closer to this point? Okay. That's what I want to know. And how are we going to do this? Well, I mean, it's straightforward over here because these are opposite sides of the y-axis. So we just have to look at the x component and decide in this particular example. Okay. So the general detection is like this. So find which constellation point Rx Ry was closest to. Okay. So in this example, all we have to do is look at the x component. So in the example, we are just transmitting either a signal here or a signal here. We are not transmitting anything on the y component. So what we do is, if Rx is greater than 0, then we detect 0. But if if Rx is less than 0, then we say that it's bit 1. Okay, we can say less than or equal to 0. Okay, and we don't care about the Ry component in this particular constellation. Okay, so how do we calculate the bit error rate? Well, it really depends on the noise over here. So we know how far this received constellation points are. Okay, if there was no noise, we know how far these constellation points are going to be away from the origin. So, and we know the distribution of nx. Okay, it's a Gaussian distribution, and so that is going to tell us what is the probability that we get the bit in error or not. Okay, so Rx we said is A times Sx plus Nx. Okay, and so suppose, so this is 0, and suppose this is A times Sx. Nx is a Gaussian distribution, so what's it going to look like? So if I plot the probability distribution function around this, it's going to look something like this. Okay, so this is a Gaussian. So what is the probability that I send this signal, but the receiver thinks that I sent the other signal corresponding to bit 1. Okay, so I'm just looking at what was received, and with this probability I get, let's say, so what does this PDF mean? It means that I'm calculating what is the probability that Rx is here. The probability that Rx is here corresponds to this probability. Okay. So what is the probability that I get the bit in error? That means that Rx actually goes negative, and that is given by this probability, right? So I just integrate the tail of this Gaussian. So the tail probability of this Gaussian distribution gives probability of detecting the bit wrongly. Okay, so just let me summarize it. So what I've transmitted is S of t, which corresponds to constellation point Sx comma Sy, and in this example Sy is 0. There's no sign component at all. But by the time it reaches the receiver, it's attenuated, so it comes a bit closer to the origin. And now noise gets added. So noise is going to push this up and possibly to the left or to the right with a certain probability. We don't care about the y component because we are not using it in the detection, right, in this particular example. So what is the probability that when this is sent, I actually say that bit 1 was sent. So remember that this is bit 1 and this is bit 0. So that's when Rx, the received signal, actually goes that side of the y-axis. It goes beyond 0. Okay, it becomes negative. And that happens when the noise, the x component of the noise, is negative and higher than Asx. Okay, in magnitude, it's higher than Asx. Okay. So essentially, I can look at this Gaussian distribution and calculate the tail probability. So what I mean is that I have a Gaussian distribution. What I have to do is I have to calculate the probability here beyond a certain threshold, okay, corresponding to this 0 over. So this is Asx, and this is 0. Okay. So it depends, of course, on what is the variance standard deviation of this Gaussian distribution and so on. Okay. So that will be known to the engineers. They will know what is the variance of the noise and so on, what is the energy in the white noise. Okay. And so they will be able to calculate this. Okay. So clearly, if this quantity is going to be most of the time much higher than this noise, then we are getting lower bit error. Okay. So this is really your signal. Of course, I am not looking at it in the time domain, but I have plotted it in this vector space, and this is the noise. Okay. And clearly, if the standard deviation of this noise is much smaller than this ASX, then we are in good shape. That means we are going to get the bits correctly most of the time. Okay. But if the standard deviation of this NX is comparable to this, then we are in trouble. We are going to get lots of bits in error. Okay. So essentially, the bit error rate is dependent on what is called the signal to noise ratio. So the signal noise to noise ratio is the signal energy or the signal power, I should say, to the noise power. And the signal to noise ratio essentially is going to tell us what the bit error rate is going to be. You can calculate this tail probability as a function of the signal to noise ratio. It's called SNR. Okay, so what is this modulation scheme that I've shown? It's actually used in practice, and it's called BPSK, binary phase shift key. So let's write down a few modulation examples. Binary phase shift key. So here the signal constellation that you are sending out just looks like this. Okay, and why are we calling it phase shift? Well, because you are shifting the phase by 180 degrees when you are going to the other bit. Okay. So let's say this corresponds to 0 and this corresponds to 1. Okay, and of course it depends on the convention. You can also switch it, right? You can say that this signal is 1 and this one is 0. Or you can even choose your constellation points on the y-axis rather than on the x-axis. Okay, so they are all examples of BPSK. So BPSK you would have a scheme in which you have both these points exactly opposite, 180 degrees out of phase shift with the other, right? And at the same amplitude as the other one. Okay? So this is what we've looked at. But why do we need to have only this? This is just sort of the simplest example. I'll just say this, just write it here, sine and cos. There's also something called QPSK. That stands for quadrature phase shift keying. So what happens here? So you might think, why only send 2 points? I can send more points, and that might have some advantage. So here I have cos and sine. So let me send 4 points. So let me send So this one is at 45 degrees, you add another 90 degrees, another 90 degrees, another 90 degrees. Okay. And now since I could send 4 signals, let me just call, I'll maybe number, let's call this S00. S00T corresponds to this. And I can assign 2 bits to each signal because I have 4 signals. So I can actually send 2 bits of information with each signal that I'm sending out. Okay. So let's say that I assign bit 00 to this. Okay, so my data bit stream is coming in. Let's say I have 11001001. Okay, so when it comes, let's say that I've somehow sent this one out. Now I send this signal out. Okay, and when I have bit 00, I send out the signal corresponding to this constellation point. Now how do I assign other bits over here? Should I assign 1 1 here? Let's think about it. So suppose the bits are 1 1, does it make sense to send this one out? So really that depends on the bit error. So how are we going to decide what was transmitted? So we said whatever is received, I'm going to see which one it's closer to. Okay. And it turns out that it's easier. Okay, so maybe let's think before we exactly look at it. So I'm going to ignore the attenuation for the moment. Okay, so let's say that this was itself transmitted and all that we have to worry about is the noise. So in this particular case, I have to look at both Rx and Ry. And I'm going to see, so suppose there was a point received here, Rx, Ry. I'm going to say that it's closest to this constellation point, so 0, 0, 0 was sent out. If it crossed here, suppose the constellation point was received here, I might think that it is this one which was sent out. Okay, so that I'm going to get some bits in error. Okay, so that would happen rarely because we said the Gaussian noise may not be that much. So if I transmit this, it's mostly going to be in the first quadrant. Okay, but there are rare cases where I go to the second quadrant or the fourth quadrant. Okay, and the chances of going to this third quadrant is going to be the least when I transmit this one. Okay, because then both x and y would have to be negative. Rx and Ry would have to go negative. Okay, and that's going to be happen very rarely. Okay, so the chances that I transmit this constellation and I actually end up in this third quadrant is going to be lowest. Okay. Now the problem with assigning bit 1 1 here is, okay, so let's think I have a choice of putting 1 1 anywhere over here. I just started with 0 0 here. Where should I put 1 1 among the 3 of these? So I said there is some chance of, if I transmit this, that I end up in the second quadrant. And if I put 1 1 over here, then I will get both bits in error because I transmitted 0 0 and I am saying 1 1. So both bits would be in error. So better than doing that, better than sending out 1 1, better than assigning 1 1 to this, let's say that I assign, so these are the bits that I am assigning. Let's say that I assign bits, let's say 0 1. Okay. So these are not the coordinates of this, right? I'm just writing the bits over here in this form. Okay. Maybe I should use a different notation, maybe square brackets. And there is some small chance that I go here too, right? So I'll put bit 1 0 corresponding to this, and chances of my going here are very low, so I don't have to worry about it too much. I put bit 1 1 over here. Okay. So it's more likely that when I send any one of these constellations, let's say this one, I might end up here or here, but I won't be going here. Okay, so this assignment of bits to constellation points, which I've shown, is a good one, because even when I go to the wrong quadrant, I'm only going to get 1 bit in error rather than getting 2 bits in error. Okay. So of course, if I transmit this and I end up in the first quadrant, I will get both bits in error, but that happens very rarely. Okay. So this is QPSK. I send 4 points. I could send one of potentially 4 points if at all I'm sending out signals. Okay. So what I'm doing here is take pairs of bits and transmit corresponding constellation point. And we detect bits as before. So what we are going to do is we are going to find Rx, Ry, and in this case, just depending on which quadrant it ends up in, we're going to say that that particular constellation point was transmitted. Yeah, and we assign the data bits corresponding to that particular constellation point, which we think is the most likely to have been transmitted. So the bit error rate is not 0. It's possible that you transmitted this, but noise pushed it to this quadrant or this quadrant, or in a very rare case over here. Okay. But if your signal is strong enough, you know that this amplitude, these constellation points are quite far apart, then it's very unlikely that the noise is going to push you into the wrong quadrant. So you want the signal to noise ratio to be high, so that this happens very rarely. Okay. So now that I've shown you BPSK and QPSK, you might say, why do I have to stop with that? I mean, why can't I go beyond that, right? So I have just 4 points over here. What if I go to another modulation scheme? Let's say that I use not just 4, what if I use 8 or 16 and so on? So there is something called QAM16, and of course you can cook up your own constellation point, right? Constellation diagram, that is a term to be used, and you'll have to think what are the constraints. So I want to keep my energy transmitted as low as possible. Let's say the government says you have to keep your energy below a certain threshold. So you're constrained by that. And then you want to design, you want to push as many constellation points as possible, but you also have to consider what is the probability of getting a bit in error. So QAM16, as you can imagine, has 16 points, so it would look like this. Okay. But now I have more points like this. So I have 4 points in each, 4 constellation points in each quadrant. So typically this has, maybe I should draw it a little bit better than this. So suppose this is, let's say, a distance, let's say this is at A over here. Okay, so normally what I do is I go to 3A. Okay, so this is A and I go to 3A. Okay, I will send out these. This is minus A and this is minus 3A. Okay, so I have 4 constellation points in each quadrant. And now you have to assign bits to these. That has to be done cleverly. Because let's say what would be received. Suppose I transmitted one of these signals. Okay, let's say that I focus on this one. So suppose this was transmitted. What is the constellation received, which I am going to get? Okay, so I am going to get something clustered around here. So what is my detection going to be? Well, essentially I have to see which particular constellation point is closest. Okay, so clearly if I cross this barrier, I am going to say that it was one of these constellation points. Okay, so effectively what I have to do, I have to find, okay, so I'll have to find out which particular region I'm going to say that this particular constellation was received, right? So the red point is what I am receiving. Okay, suppose the black mark is what I sent out, that constellation point. One of the red dots is going to be received, okay, with a certain probability. Yeah, I'm ignoring the attenuation due to the channel over here, right? Just for simplicity. Okay. And essentially, if I look at what is closest to this particular point, it is going to be this region over here. So any point within this region is closest to this constellation point. So I'm going to, if I receive a constellation here, I'm going to say this one was transmitted. Right? And similarly, what about this? So here, these points in the corners are going to have regions a little bit different. It will look like this. Anything in this region, any receive point here is closest to this point. Yeah, and you can do that for all of these. I mean, you can find what is the closest region to this. Okay. So, of course, in practice, okay, before that, how many bits can you send on each of these constellation points? Since you have 16, right? So, how many can you? So, you can send 4 bits, right? So, you have 2 to the power of 4 points. So I can send 4 bits of data with each constellation point. Okay. And of course, you can go much beyond this. There is a QAM 256, for example, where you send 8 bits per constellation point. So the question is, what should you use in practice? I mean, clearly the more constellation points, the better in terms of bit rate. You're sending more and more bits. But what's the negative point of sending more and more of these? Okay. So let's talk a little bit about that. What constellation to use? So it really depends on 2 factors. One is the allowed transmit power. Okay, so essentially you want to keep your bit error rate low, right? And one of the that depends, of course, on the signal to noise ratio. So the signal power is controlled by, let's say, the government regulations. The allowed transmit power Also you want to know is what is the received signal power. Okay, so finally, of course, it will only depend on the received signal power, but these two are related, that if you can transmit more power, you can also increase the received signal. Okay, so your bit error rate, this is not, bit error rate is a function of SNR. So let's think about it. So there are several options. So suppose, let's say that the attenuation is fixed. Okay, so you are allowed to transmit at a particular power, and the signal gets attenuated by some amount. So let's look at this QPSK versus QAM16. Suppose you had a choice between those, right? Whether you're sending 2 bits per signal that you're sending out, or 4 bits. So what is the received constellation going to look like? So in both these cases, so the received constellation is going to look something like this. Okay, so if these are the, if I'm sending any one of these, then the received signal might look something like this. Okay, that's a nice constellation diagram. Now I'm constrained to use the same total power here. So the transmitted, or let's say the received signal power is the same. Okay, so I'm assuming that in both cases, suppose the attenuation was the same. Signal power the same, just remember that here these are the 4 constellation points, just the center of this. So these are the 4 constellation points that I was sending. Okay, yeah, and or let's say for a particular attenuation, this is what I would have received if there was no noise. Now I have to space these constellation points so that the average power is the same as in this particular case, right? So the government says the average power you send out is the same. So notice that both these have the same average power that I am sending out, but here these constellation points are much closer to each other than over here. Okay, in the case of QPSK, I could have each only just one point in each quadrant, so they were at some distance from each other. Here these points have got squished together because I was constrained to have the same signal power. And because these are closer than here, so these are closer than in QPSK, the bit error rate is going to go up. So I'm going to have a cluster of, so suppose one of these was transmitted, let's say this one was transmitted, then what would I have received? I would have got something around this, right? And it's very easy to get pushed into the region of this particular constellation point, and so I would get some bits in it. So higher modulation rates, so this has higher modulation rate than this one. Okay, so BPSK is the lowest, and it's the slowest, I should say, because you send fewest number of bits per constellation point. and then of course higher than this is QPSK, and higher than this is QAM16 and so on. Okay, and there are multitude of different sort of modulation schemes that you can think of. Right? So in general, you want to have the highest modulation scheme, but which meets the bit error rate criterion. Okay, and it depends on various factors. It depends on how much power I can transmit and the attenuation. Okay, because that really tells you what your received constellation point is going to be, and of course the noise power. Okay. So I should add here the transmit power, the received signal, and that depends on the attenuation and the noise. Okay. So your Wi-Fi, sometimes if you're, let's say, close to the access point, Wi-Fi access point, you can transmit data at a higher rate. You might notice that. But if you're far away, then your transmission rate actually goes down. So what your Wi-Fi card is constantly doing is it's going to look at these constellation points and it's going to see, you know, if I transmit using QAM16, what is my bit error rate going to be? Okay, so it knows the signal to noise ratio, and if the signal to noise ratio is high, then it will try to use something like QAM16 or even QAM256. But if the signal to noise ratio goes down, it will drop down to something like QPSK or BPSK automatically. Okay, and that adjusts the bit rate. Okay, so that is the raw bit rate between your Wi-Fi card and the access point. Okay, but actual data rate you get at the application layer depends on so many other things, because there's TCP in between and so on. Okay, so we'll continue the discussion of this in the next lecture.